Welcome to the webinar on HVAC humidity control with Altaire Systems, an Academy Energy Group technology. Presenting today will be Bill Steiner, the Director of Engineering for Altaire Systems. Bill has extensive custom air handling design experience and will present the technical portion of today's presentation. Greg Harrington is the Vice President of Altaire Systems. Greg has extensive manufacturing experience, including both aerospace and nuclear. Greg brings great manufacturing knowledge along with the project management rigor as a PMP from the Project Management Institute. He will present some of our projects and case studies today. Today's objectives are to review the following. Why do we need to dehumidify? Methods of dehumidification. What is decoupling? How is decoupling more efficient? How do we decouple? Why do we need to reheat? How can this methodology be deployed? What are real-world examples?
And what we want to do is we're going to have a technical session today that's going to be led by Bill Steiner. Bill is our Director of Engineering. He is from the Cleveland, south of Cleveland area, down closer to Akron. And then Greg Harrington is our Vice President of Altaire. Greg is going to be talking about some of the specific case studies that we've had. Some of them were with GSA, NAVFAC, and then the VA, so healthcare. So I think there's some people that are in the healthcare business on the call here today. So thanks for participating. And then along the way, you might see a little survey question that pops up here and there. If you want to answer those survey questions, it helps us kind of pull a little bit to get a little bit of a feel for what you're looking at, what your experience is, and whatnot. But what we'd like to do here is I'm going to hand it over to Bill Steiner. He's going to walk us through the technical portion with the Altaire HVAC adapt system. Bill, you want to take it from here?
Thanks, Andy. So just a brief overview of what we want to talk about today. First of all, what is ADAPT? ADAPT is, and why do we need to dehumidify? What are methods of dehumidification? How do we decouple? And how is decoupling more efficient? What is a desaturation coil? How does that work? Why do we need to reheat air when we're using subcooling to dehumidify? How can we deploy this technology? And lastly, Greg's going to round us out with some case studies of real world examples where we've installed this. So what is ADAPT? It is the Advanced Dehumidification Airstream Pretreatment Technology. That is what ADAPT stands for. So why do we need to dehumidify? How do we find ourselves in this position? So that is because of ASHRAE 62.1 and the requirement to bring in outside air. So typically, if you actually look at the spec, there is about 3 pages of based on your occupancy, space use type, and all of those things, how much ventilation you actually need. But generally, we say it's about 20%. 62.1 also outlines a max dew point for the space of 60 degrees. And our target is generally 55 degrees dew point leaving the air handler. Sometimes we're lower if we have process constraints and things, but it's that bringing in of outside air is where we pick up humidity, right? Sometimes there is a latent gain from the space. If we have a poor building envelope, or if for some reason we've got a process or something in that space that is putting humidity off into the air, that could also contribute, but the predominance is from outside air. So why is that important? Well, typically when we think about a humid area, we think about the southeast, the areas that we see in red, maybe that pinkish color. But really any of those colors, even up into the yellow, they're going to have to dehumidify when they're bringing in outside air in the winter, or I'm sorry, in the summer. We typically don't think about those areas as much because they have a heating component or a winter season that is equal to the summer. So when we think about needing to dehumidify and that being a year-long requirement or a requirement of highest importance, that's typically again in the Southeast. But I want everyone to be aware of the simple fact that pretty much anywhere east of the Rockies, you're going to need to be able to dehumidify when you're bringing in outside air in the winter, in the summer, excuse me. And why do we need to dehumidify? Because we don't want our buildings to look like this, right? We get an excess of moisture in the space that leads to mold. It leads to all sorts of health issues. We get rusting of diffusers, wallpaper peels off. These are some extreme examples, but this is what happens if we don't adequately address the need to dehumidify our air. So what are some common methods? Really, there's two methodologies, right? We can use a desiccant system, which absorbs the moisture out of the airstream, or we can subcool, which in subcooling, we're just taking that air down to a temperature where there's no more space in between the air molecules for moisture to be entrained, and that essentially wrings all the moisture out of the air. Purposes of today's discussion, we're going to talk about subcooling, and I believe that these pictures represent a pretty good visual of the complexities of using desiccant versus the simplicity of using subcooling, right? When we talk about subcooling, it is how do I make this airstream cold enough to get to a dew point that I want? When we talk about using desiccant, we talk about regeneration cycles, reheat for reactivating the media, or if we're talking about liquid desiccant, we've got all sorts of pumps and regeneration and things that go into that. So complex versus simple. So when we specifically talk about chilled water, subcooling, how low can we get? What's the minimum dew point that we can achieve given a water temperature? And again, obviously that depends upon design conditions. There's several factors that go into this. What are our outside air temperature? What's the max allowable water pressure drop on our coil? What phase velocity are we running that coil at? And how much air pressure drop are we going to allow on that coil? I've made some assumptions on the left to come up with this chart, but what you'll see is that we're 2.5 degrees, roughly is the closest we can comfortably get on approach to our water temperature. So what that means is if I have 46-degree chilled water, I can get down to about 48.5 degree dew point with that chilled water. So something to keep in mind when you're thinking about using chilled water for the sake of dehumidification, and maybe you have a more stringent dew point than the typical 55 degrees leaving, you can get down to a much lower dew point than that, depending upon what chilled water temperature you're able to provide. So what is decoupling? Simply put, decoupling is when we have a mixed air unit, we have outside air, we have return air. We know that we need to treat that outside air, right? Unless we're in an economizer mode, we can't bring that outside air in and be able to just directly put it into the space. Decoupling is treating that outside air before we mix it with the return air. And I have a couple examples of peak and part load days where we compare decoupling with mixing the airstream before, and you'll see it's much more efficient because, simply put, if you think about how much outside air we're bringing in, again, typically 20%, takes a lot less energy to treat that 20% of outside air before I mix it with the other 80% return air than have to treat 100% of my supply air volume. Some additional advantages to decoupling is because it's robust. Again, we're using a chilled water coil. It's pretty simple. It's pretty forgiving. You can take full advantage of supplier temperature resets. If you recall back to the two different methods that we can use for dehumidification, desiccant systems, things like that, aren't as tolerant of being set back as far as something as simple as a system that utilizes subcooling. Again, because it's a simple system, it's a really low cost of ownership. When you compare out initial costs as well as life cycle cost analysis, desiccant systems with a subcooling system using chilled water, it's much more advantageous in the long run from an O&M standpoint to go with the simpler system, right? Um, Additionally, because of the simplicity of it, and we'll get into some more specifics in this later on, when you're looking at a system where maybe you don't want to replace the AEG, it's still got a lot of life left, whatever the case may be, it's much simpler to retrofit this technology. You're talking about adding a plenum, a coil, some filters to protect that coil, and you don't have to try and figure out how am I going to get a wheel into a unit that was never designed for a wheel, right? So, any questions so far? Okay. So let's look at some example data comparing decoupling and its efficiency. So this is a peak sensible day. Our criteria here is we want a 56-degree supplier temperature with a 55-degree dew point. At the top, and this will be the same setup for all of these slides, at the top you'll see just the setup where we're not doing any pre-treatment of the outside air. We're going to bring that in, mix it, and then do our cooling and dehumidification. So we have 92-degree outside air with a 2-degree dew point. Mix that, gives us 77.5 degrees with a 58-degree dew point. Great. I've got to cool all of that down now to about 54 degrees to make sure that we've got a little buffer on our dew point. And then our supplier fans are going to give us a couple degrees heat. A fan will put us right on target for our supplier requirements. Now, in the bottom scenario, we're going to pre-treat that outside air before we mix it. So when we pre-treat it, that's going to leave the adapt coil at 54 degrees dry bulb with a 48-degree dew point. When we mix that air with the return air, and again, same return air is in the first scenario, that's going to give us 70-degree dry bulb with a 52-degree dew point. Great. I don't have to worry about dehumidification at this point. My dew point is already meeting or exceeding the required set point. I just need to apply a little bit of sensible cooling. And then again, I'll pick up that couple degrees, heat a fan, and I'm right where I need to be for my supplier temperatures. Keeping in mind that this is a peak load day, and when we design, peak load days are our worst case scenarios, but when we talk about energy efficiency, we see the biggest gains on the part load day, because peak load is everything we've got to meet requirements on the worst day of heating or cooling that we're going to see over the year, right? So keep that in mind when we look at combined chilled water consumption. In the first scenario, we're using 146 gallons of water per minute to meet conditions with the given outside air and return air temperatures. Versus when we use outdoor air pre-treatment and we treat that outdoor air before we mix it, now we're only using 76 gallons per minute. That's nearly 50% reduction. And it's for no other reason than it's simply more efficient to treat that outdoor air before we mix it with the return air. Are there any questions on this before I move on to a part load day example? So we look at the part load day example, and remember, I mentioned that this is where we're really going to see the energy savings. So we're looking at an outdoor air temperature of a 77-degree dew point, or 77 degree dry bulb with a 66 degree dew point. Same return air temperature. In this case, because it's a part load day, we need a 62 degree leaving air temperature. Again, though, with a 55 degree dew point to meet space conditions. So first scenario where we're not using outdoor air pretreatment, we're going to mix that air with a returner that's going to give us 74.5 degrees with a 57 degree dew point. We have to subcool that entire air volume now because we're over our dew point. We've got to cool down to about 54 degrees to hit that. We'll get a little bit of heat of fan, but now we're too cold for our space conditions, right? So somewhere along the way, we're going to have to apply a little more reheat to this to get us up to our 62 degrees. We need about 6 degrees of sensible reheat to meet conditions. So same scenario down below, except this time, again, we're going to do pre-treatment. And again, we're leaving the adapt unit at 54 degrees with a 48 degree dew point. Gives us a mixed air temperature, 70 degrees dry bulb, 52 degree dew point. And great, now we don't have to worry about any dehumidification. We've just got to do a little bit of sensible cooling, 10 degrees to account for the 2 degrees we're going to pick up from our fans. And that puts us leaving at the temperature we need. So what does this mean from an energy and water consumption savings? Okay, now we're looking at 125 degrees or 125 gallons per minute when we're not pre-treating versus 42 gallons per minute when we do pre-treat. Again, reasons are the same as we've already explained, but especially on a part load day, it's a very powerful way to reduce chilled water consumption. Any questions? Okay. So what is a desaturation coil? How does that work? The easiest way to think about a desaturation coil is it is a chilled water coil in front of a hot water coil. And the way this works is we're going to take chilled water in, we're going to perform our cooling on that outside air, and we're going to take that leaving water temperature and we're going to put that leaving water through a heating coil now, and we're going to put some of that heat back into the airstream. And this does several things for us. One, when we talk about 90.1, this is where we get our compliance for 90.1 in 2 ways. 2, because we are rejecting some of that heat back into the airstream because we need that reheat, it allows us to use a higher delta T on the cooling side of the coil, typically 25 to 35 degrees. But then our overall delta across the coil, again, because we're putting some of that heat back, is going to be 20 to 25 degrees total delta T on the water side. So what that means is because we can reject more heat into that water, we need less water, which is less water consumption. So another way that this is an efficient system. Is there any questions on how a desaturation coil works? Okay. So why do we need to reheat? Well, we don't want the inside of our handler to look like this. If we don't reheat, if we send fully saturated air through the system, we run the risk of having standing water. So anytime we have fully saturated air and that crosses a pressure differential, filters, coils, anything in your unit that requires some amount of static pressure to run, there is a high chance that you are going to have some of that water fall out of the airstream and start to puddle in your unit. Typically, the first thing we see after a mixed air mixing chamber, shelf mixing, whatever you're doing there to mix your air, are the filters. Those are probably the worst thing that could have fully moisture laden air to hit them, right? Because they're a breeding ground for Mold bacteria, we have a pressure differential there. So will wring the moisture out. You might be wondering, well, hey, I'm bringing this return air in. I shouldn't be fully saturated. That's true if you have fully mixed your air. And even in scenarios where we're using air blenders or you've got shelf mixing or some sort of dedicated way to make sure we're really mixing the air, it's never truly 100% that you've fully got complete mixtures and you're not going to have a pocket somewhere in that airstream of the fully saturated outside air. So that is why it's really important to reheat as soon as possible. So, we talked about this a little bit already, but ASHRAE 90.1, how is this compliant with ASHRAE 90.1, which is the standard for energy efficiency? Um, so first of all, when we look at 6.5.2.3 for what is allowed for dehumidification, you're not allowed under ASHRAE 90.1 to do simultaneous heating and or cooling of the same airstream. So what that means is we can't subcool with chilled water and then have hot water or some other means of providing reheat that requires additional energy inputs in the same airstream. Now, there are several exceptions to that. The two that we'll talk about are the two that are applicable to this technology, and that is exception number one. And essentially, what exception number one is saying is if you decouple, if you're only doing that simultaneous cooling and reheating to 50% or less of the airstream, aka just the outside air, then you're allowed to do that simultaneous and cooling and reheat because it is much more efficient to only apply that to the minimum outside air requirements. Additionally, exception 5 also allows for you to do this if you're using at least 90% site recovered energy to provide that reheat. So again, in this case, if you remember back to us discussing the desaturation coil, 100% of that energy for the reheat is provided through waterside energy recovery, and it is fully compliant with 90.1 in that regard. So we meet both those exceptions. Additionally, if you look at 6.5.6.1, there is a requirement for exhaust air energy recovery. We won't read through all of this. However, there is an exception to this requirement, and that exception is if you are in climate zone 0 through 4, um, and you require dehumidification, which you definitely will if you are in those zones, you can employ series energy recovery, waterside recovery, like we do with our technology. And you're exempt then from having to have that exhaust air energy recovery. Is there any questions on 90.1 before I move on? Okay. So how can we deploy this technology? Essentially, the easiest way to say this is any application where you could dream up an air handler, I can get this technology into it. So if we've got a new application, new building, we're building new air handlers. You can see in the model here, we've got a mixed air unit with our return air on top, our outside air on the bottom, and our outside air plenum, we have the adapt coil. Built right into the air handler. This can come as you would order any other air handler with any other equipment, accessories, options, what have you, that you would order with any custom air handler with the adapt technology built right into it. As we talked a little bit before about the advantages of using this type of technology, retrofits are super simple. So in this case, the dark brown colored unit there would be an existing air handler that has chilled water supply to it already. And a little light gray unit on front of it, the adapt unit there, would be a retrofit. And all we need to do in this case where we want to retrofit is we install the adapt unit. We duct from the adapt unit into the outside air intake of the existing air handler. We take some saddle tees and take off a little bit of chilled water supply from that coil and the existing air handler, and that is enough water for the adapt coil. And then we plug in our Ethernet and give it 120-volt power, and it's ready to go. It does come with onboard pre-programmed controls, so it's about as straightforward as an installation's going to get. Additionally, I don't have a pictograph for this, but if you can imagine the first scenario, this one here where we have a custom air handler, this would also apply to a DOAS. So if you have a situation where you need a DOAS, you want to employ this technology, it's no different than building a custom air handler, a mixed air handler. So what are some standard construction details that we use that we feel are important when we're talking about dehumidification and wanting to hold up and be robust for the long term? So our units as a standard are going to come either all aluminum or stainless steel construction. Surprisingly enough, right now it's about the same to supply stainless steel as it is aluminum with all the tariffs and everything going on. So fun little fact. Additionally, when we do our adapt coils, because we are putting them into the nasty moisture laden air in coastal applications, this is also salt moisture laden air. We're going to put a coating on that has a 10,000 hour salt spray rating. Again, that comes standard. We want this thing to last 40 years without needing to be replaced. One of the other ways we help that effort is we keep the face velocity on this low. There's several reasons for this. One, because we're only doing outside air, we can have a lower face velocity in the same footprint as if you think about a mixed air unit that I showed you a couple slides ago, our filters and coils are going to kind of set the size of that unit at 500 feet per minute, 450 feet per minute, whatever we're designing to. They kind of define that cross section of that unit. Because I'm only doing 20-30% outside air, I could have a bigger coil that still fits within that footprint and run it a lot slower. Additionally, that helps me with performance, right? The slower we run a coil, the better performance we're going to see across it. The more that helps with air pressure drop, right? So part of our mission here is to save energy. It makes no sense to run that coil any faster than we have to, and take a penalty by the way of an air pressure drop. Lastly, because we're wringing a lot of moisture out of the air, the slower we run that, the more we reduce our risk of carryover. So if we're running at 500 feet per minute, there's all this crazy water coming off this. It's a really humid day. We've got like a 75-degree dew point or something crazy. We're running at 500 feet per minute. We're bringing gallons of water out of this thing every minute. You're going to get carryover. And again, the next thing downstream is typically the filters, and those are the last things that we want to get wet. Not that we want moisture anywhere in the unit, but the filters are the worst things to get wet. So again, another good reason why we run this nice and slow. So before I get into some other technologies on how we can do energy recovery, does anyone have any question?
Got a question. So
Yeah.
how common is it for these units to come with preheat coils for no other reason to keep your cooling coils from freezing?
So in ours, typically the way we approach that, unless it's a DOAS unit, even then, we would still employ the same thing. So we would use in a climate where we would need to have a consideration for wintertime and heating, we would use the adapt coil as a swing coil, and use an exhaust air energy recovery coil to supply preheat to that coil. And then that gets us energy recovery in the winter. It takes care of our freeze protection on the coil, and just seems to be the best approach forward. But again, if we need to put a hot water coil, steam coil, unit heater, whatever in front of it, we can do whatever you need us to do in that regard. Any other questions? Okay. So what are some other common methods for dehumidification and energy recovery? We'll just quickly go through these. So wheels, probably the most common thing out there. Energy recovery wheels being the most common type of wheel. It's a little less common that you see desk wheels, but they both have the same problems, right? There's a lot of moving parts. And there's a lot of pitfalls. Maintenance is expensive. Seals are important. If we don't have good maintenance, we don't take care of our seals, we get leak by, we get less efficient performance than we did the day it was commissioned. And we've got an expense. We've got a long-term expense. If you take manufacturers at their word, every 10 years you're replacing media. I think in practice, most of us have found that that's more like 5 to 8 years. So you think about a life cycle cost analysis, how many times we're going to have to replace media, the annual upkeep of something like a wheel. It's not a cheap proposition to put a wheel in a unit. So runaround coils, again, I've kind of mentioned this already. In the winter, we would employ this too, where we need to have energy recovery. These work just fine. They're efficient. However, one thing to note is this is not a means of dehumidification. So if you're employing this as pre-cooling, preheating, that's great. You're going to get some energy recovery, but you're still going to have to subcool all of your air volume or have a secondary means of subcooling just your outside airstream if you choose to decouple, because this won't get you down to the dew points that you need to get to. Plate heat exchanger, it's pretty similar methodology to runaround coil. We're converging airstreams. We're taking heat from the outside air and we're rejecting it to the return air or vice versa in the winter. Except this is done in a more compact yet less flexible footprint, right? I have to have a unit configuration like you see in the diagram here in order for this, all four of those airstreams to converge. Whereas, a runaround coil loop, you can have your exhaust air somewhere else, vetted somewhere else, and your only limitation there is piping and pumping. Again, just like with the runaround coils, it does provide energy recovery. However, you're still going to have to subcool everything to get down to your dew points because you're not going to get there with a plate heat exchanger alone. Wraparound heat pipe. Couple quick thoughts here. One, this only is going to provide energy recovery in the summertime when you're cooling. It does provide a little bit of reheat, but you're not getting the advantages of decoupling, and now you've got essentially 3 coils, so a pretty high static pressure loss, where you could accomplish the same work using water side recovery with just 2 coils. Liquid desiccant systems, again, we talked about this kind of in the beginning. They're complicated. There's a lot of components to these that can break. There's media that can become fouled, and render the system either useless or certainly degraded performance compared to commissioning. These that haven't really been out quite long enough to get a good handle on what are their life cycle costs in terms of how long does this media really last. What kind of component failures would you see over the course of 20, 30, 40 years? So they're also a little bit of an unknown. Any questions so far? Okay. So how do we save energy? Just quickly summarize this for everyone. So again, decoupling, when we treat latent and sensible loads separately, when we don't mix all of that air before we need to subcool the return air, outside air, um, it's obviously much more efficient, as you guys have seen today. Um, Using the integrated heat recovery for reheat saves us the energy to have to do reheat, whether that's in the unit with some hot water, whatever means you're using there, or if it's in the space of a VAV box with a hot water coil, an electric coil, what have you. Um, it's more efficient when we're getting that reheat for free, right? Um, Also, again, one of the biggest ways that energy is saved is through chilled water reduction. Um, because we're being more efficient, as we've discussed with our design, we're able to reject more heat. We're decoupling. It reduces the load on the chiller plant. Um, and again, you can also take advantage of supplier temperature resets. So in an area where you don't have full-time occupancy, you're able to set back more. And the more you set back, the more energy you're going to save in those off hours, right? So there's a lot of ways that this can help save energy on a project. Um, Lastly, you don't have to take my word for that. We do have an 8760 tool. We'll pull NOAA data from the nearest weather station of your project. We will put that in a spreadsheet that does all of the calculations based on enthalpy. And that's going to tell you what you can expect to save on an annualized basis based on current utility rates. Up next, Craig is going to present some case studies for you where we have installed this technology.
All right, thanks, Bill. What we're talking about today are some projects that we run with the help of the federal government concerning validating the technology. So a couple of programs that we are involved with are through the Department of Energy High Impact Technology Catalyst Program and the GSA Green Proving Ground. So these projects are like we said, funded by the federal government to try to understand how to improve building performance with new technologies. So for the Department of Energy, they have a building technologies office, which sole focus is to find ways to make buildings more energy efficient. And so they actually have a couple of groups within that building technologies office called the Emerging Technologies Collaborative for Buildings and the Better Buildings and Plants Initiative. And so there is a group heavily invested within federal space on trying to find ways to take that typical 30 to 40% of a building's energy consumption for HVAC and reduce it, at least for the validation projects we were part of. And the same thing goes with the GSA Green Proving Ground. It's part of the Center for Emerging Building Technologies, which is out of their recently reclassified Office of Engineering. But it's the same approach. It's the idea that because GSA is the biggest portfolio owner of buildings in the United States, how can they save energy? So these validation projects are something that you actually apply for. You go through a submittal process that's reviewed with the help of National Laboratory. You go to a semifinalist round where you then are interviewed, and then there's final selection. So we were fortunate enough to get selected for these. Our high impact technology catalyst program is in Orlando at a Navy site. And our GSA Green Proving Ground award-winning project is in a courthouse in East Texas. So talking about what's going on in Orlando. So the facility was having humidity control problems where, especially on high humidity days, they lost control in the building. And it got so bad in certain cases that there was condensation issues, quote unquote, rain coming from the diffusers on the upper floors. And so when they were investigating this further, they were taking a look at the amount of outside air that they were actually dealing with. And so part of what they recognized is that the original building design didn't meet ASHRAE 62.1 requirements. And so they know they weren't properly ventilating the building to begin with based on the occupancy. So when we went out to site to actually do the site survey to try to better understand what was going on, with their air handlers, we actually measured it closer to 4,000 CFM, which was grossly underestimated. So part of their problem, because they couldn't control the humidity, the building operators made decisions such as, we're going to close our outside air dampers because we can't deal with the humidity. And in the end, they were actually driving that building to be negative pressure. So there was more building envelope leak through, bringing humidity into the building, just making the situation worse. So this site was looking for a way to improve their humidity control without making drastic changes to their existing air handlers. They had plenty of life to them. They weren't looking to do major building envelope reconstruction, even with these units being up in the penthouse, having to go cut major accesses in and out of the penthouse. They weren't interested in doing that. And so they identified a project where they were going to upgrade their existing HVAC controls to help improve energy performance. And they were able to fund this project with our technology to piggyback along with that. And really what this is a great example of for folks on the retrofit side, utilizing sustainment funding and combining projects to create value is exactly what the site energy manager did at this Navy facility. And he was really innovative in being able to identify, okay, I've got multiple problems I'm trying to solve. I can take the approach of, here's what I can do with my controls. What can I actually do with my mechanical equipment to improve their performance? And that's why we were such a great fit for this. So once said and done, our units are installed. What we've been able to do is increase the percentage of outside air for the building to meet ASHRAE 62.1 compliance. So we basically went from 4,000 CFM measured to roughly 34,000 CFM currently being ventilated into the building. And so really the question is, and the assumption to challenge here, and again, this points to what Bill was talking about on the efficiency gains of decoupling. The gut reaction is, well, if I'm increasing my outdoor air percentage, I'm going to increase my energy usage. And so because this is part of a federally validated project, we just recently have the initial draft that's going to be issued later this year. Air handler savings alone for the unit that went through the validation process, we saw roughly a 40% reduction in energy consumption. And that's a significant impact on the AHU level, but trying to understand what was happening at the building overall, we were also able to get information concerning total kilowatt hours consumed. And this is where we saw a huge savings. Roughly 18% of the whole building energy consumption, over 1 million kilowatt hours annually, were saved by utilizing this decoupling approach. And again, because we didn't do anything from a major construction point of view, this was able to be funded through the sustainment side of the operation. And just as critically important as the energy savings is the idea of what that did to the indoor air quality and to, occupant comfort. And so part of the real-time feedback that we've been receiving is that this building is noticeably different with the ADAPT pretreatment units pre-treating the air to the air handler. So what does that actually look like? For us, in this case, 7 air handlers on the roof. We weren't in a position where we could easily put one DOAS unit to feed multiple air handlers. So the most effective strategy based on the demands that the zones had for each of these air handlers was to apply our pretreatment unit. And that pretreatment unit, based on the capacity within the air handler itself relative to static, we were able to just supply coil and filter units without the need to augment any fan. So to give you an idea of kind of what this looked like according to BAS data, a real-time snapshot, if you look in the upper left-hand corner, you can see this is a morning day in August. Very humid out, 82-degree dry bulb, 72-degree dew point. And really, this is where condition that we excel at. Because again, what Bill was referring to, when you're treating just a small portion of the total airstream, and you're able to do all your latent cooling, and the fringe benefit here of driving down to that dew point that we needed to make sure when it mixed to the building return air, it was already at the supply air set point that it needed to be. The fringe benefit is we're actually doing all the latent cooling that we need to do. So based on this scenario, the loads coming back on the return air side, we were able to do all of the conditioning on just the outdoor airstream component, so that when it mixed with the return air, as it went through the air handling mixed air coil, that mixed air coil for this scenario at this time was not doing any work. And that's, again, where you can recognize the savings. And really the big impact here as well with the energy recovery for this site in particular, they were having consistent issues on their reheat loop relative to valves, relative to boilers, where they went through an extended period where those were completely taken offline. And we were able to sufficiently keep a 300,000 square foot building in the appropriate dew point set points in the building without any additional reheat or independent reheat through the high part of Florida humidity season. Does anybody have any questions relative to this project? And Bill was also talking about, the application and where we can apply this. It's really dependent on the site need and the issues that the client's having. So in this case, our next project was for a VA up in Western Massachusetts. It's an area that you're probably not thinking there's a ton of humidity. But in this case, at the high points in the summer, with the current DOAS that they had on site, they had to continually shut down their sterile processing department because they could not condition the amount of humidity in that outside air and ensure that that sterile processing department met its operating requirements. So in this case, this is a great retrofit where we had an existing pad, we had an existing ideal footprint that we needed to be able to design our unit to. And in this case, they were also looking to increase the amount of spaces that their previous air handler couldn't cover. So this was a great opportunity, again, from a retrofit point of view of being able to plug our unit in and be able to control humidity. And so this unit is, like Bill was saying, we've got options on, depending on where your equipment is located. In this case, we used a hot water coil for the preheat. Because this was a DOAS and it was in New England and it had wintertime issues, along with obviously the fans and the VFD, we had steam humidifier coils in here, just because in New England it can get really dry in the wintertime, and we still had to meet that sterile processing department relative humidity requirement. And one of the things we've utilized previously in our projects to try to eliminate biofouling on our coils is we use ionizers. And we have the ability to tailor that. If you've got preferences to UV or things like that, we can adjust and work with you to meet those requirements. But this unit in itself is, again, providing and meeting the mission that it was designed for, a very specific application that the client needed. In our final project, again, a retrofit opportunity. This was unique because it was in East Lufkin, Texas. It's a smaller building. They had insufficient ventilation, couldn't meet their outdoor air requirement. This case, we had 3 small air handlers, all sharing a single outside air duct. So we were able to put our unit on the outside air duct to condition all of that air before it went to those air handlers. And again, we're able to maintain humidity control by doing all of that latent work up front based on the highest demand on the zones. We're able to get that air conditioned so that when it goes through the air handlers, it's only getting any kind of sensible trimming it may need. So in this case, we went from, on the left here, you can see the bowed ceiling tiles on the courtroom. We're able to put our unit down in the basement, the 2500. And again, this unit had a coil section, a filter section, and this one, because it was feeding multiple air handlers, we had a fan VFD section. And we had to bring it in modules because of the access to the equipment room. So we have the ability to get these things through standard doorways by the way we do our shipping splits. And so when good approaches to technology are recognized, we were fortunate to partner with Searle when they were developing the most recent version of this Resilient Energy Systems design guide. And so things that they talk about in this design guide are the focus of our approach. The idea of how you're constructing constructing units relative to coastal locations and humid locations. What you're doing with your filtering, especially in corrosive environments. Really, the big ones are, the idea that it is important to decouple your loads. And the idea that when you're decoupling and you're conditioning air on that outside airstream, that you need to temper it, that you need to ensure that you're bringing it well off of that saturation line. And pointing out to energy recovery that's got to be compliant with 90.1 to include waterside recovery. And so we were on the ground floor of, hey, look at this approach, bring this approach. People typically see this as a DOAS, but this document was specifically written to say DOAS or outside air pretreatment. And so we're actually published within this document as a viable way to manage humidity control in hot and humid environments. And one of the things that, are always important when you look at these design guides is seeing who's contributing. Both Academy Energy Group and Altaire provided input into this. And really, we also got recognized for being, doing some work as far as actually helping generate content and provide industry expertise into this document. All right, any last questions? We kind of wrap up the presentation, but does anybody have any questions right off the bat? With this, really, you can hear us talk about the success in projects. You can hear us talk about how we're validating things. Bill mentioned we have the ability to do energy calcs and give you a modeled idea of what to expect. Really, that's what we're all about. Like, we understand learning about a new technology, learning about a new approach. And really, in essence, I should rephrase that. It's not new technology. Decoupling is not innovative. They've been doing it with DOAS units. Desaturation coils is not innovative. They've been around since the 90s. What's innovative is how we are applying it to provide value to clients. And so really part of this is we're looking for people to bring us projects so we can show you. We have a rough idea. We have a rough template of information that we would need to help come up with some preliminary footprints, layouts for equipment, budgets, a preliminary energy calc, so you can see for yourself. And part of the follow-up we will do after this presentation is to send a copy of this presentation, the design guide, our project evaluation sheet, and give you a follow-up after this presentation is done. And then you can always check us out on LinkedIn or on the web. And with that, I'm right at the time. Any final questions? All right. I just saw one come
Came
in.
into the chat, Greg.
Let me just open up my chat here.
Here, I'll read it to you. So have you guys looked at what annual energy savings would be or life cycle cost amount of LCCA for the 3 projects?
So the life cycle costs, we have not done a deep dive in for any of these projects. What was most important for the stakeholders at the time for all 3 projects was I have humidity I can't control. I need a solution for that. And then the fringe benefit has been on the actual validation on the performance, on the annual performance, on the reduction on energy. So the things that we really have not gone in and officially value, but see the difference is on the maintenance and operations annually on our unit with compared to any unit with the energy recovery, because it's just filter cleaning or filter change outs and coil cleaning, you're going to have a lower maintenance cost. And the same thing that Bill was referring to on the life cycle. We're going to see an improved life cycle because you're not changing out media and you don't have rotating moving parts. Does that answer your question?
Yeah, for the most part, it does. I was just the last part was do you guys know what energy modeling software would you recommend to like model your all systems with?
So what we have is I'd call it a homegrown, but it's an 8760 tool that uses an enthalpy add-in from Excel that's available. And what we've actually reviewed, because we're doing a lot of ESCO work, we've had energy performance folks review our calculation and say it's a viable tool. And what we're seeing relative to what the folks at the national laboratory level are in line. Like we had a modeled energy savings for a building in Atlanta that was roughly 16% energy savings through a very intense model versus what we're actually seeing in that from measured actual results in our Orlando building. So
Yeah, I
we're,
think
Go ahead.
MREL used for the model for that Atlanta. I think they used Energy Plus, and then as Greg mentioned, we have the 8760 tool that dials it in a little bit more accurately based on all the math. So you could also contact us to assist you with pulling that together.